last lecture, we started discussing critical angle. Now let's solve few problems. Okay, few problems on critical angle. Note down all the problems. Try to solve it on your own. Okay, and let's see. And of course, you can solve it on your own. Okay, let's see if you get the right answer in your first attempt. Okay. Just remember one thing. Just remember one thing. Whenever light goes from denser to rarer medium, you always have to be careful, very careful. Okay. Light going from rarer to denser, no problem. Normal refraction will happen all the time. But if light goes from denser to rarer, at that time you have to be very mindful, very careful. Okay, the critical angle, total internal reflection should be the things appearing first thing in your mind. Okay, so let's look at the first question here. Net deviation. Okay. On the first surface here, this is a normal incidence. It's normal incidence. Will there be refraction or not? First surface here, do you think there will be refraction? Light is incident normally. Okay. There will be refraction, but no deviation. Light passes without deviation, undeviated. At this point again, there will be refraction. There is change in medium. Okay, this is glass, some medium. And this is air. Light is going from denser to rarer. Mu is given. Mu is 1.25. So here I have to be careful. What we will do is, let's calculate critical angle first. Critical angle, okay. Sin theta c, critical angle, is mu rarer over mu denser. This is 1 over 1.25. I can write as 5 by 4, okay. So 5 over 4, this becomes 4 over 5. What will be theta c? It's a standard angle. Theta c will be 53. Critical angle is 53. Now, this is 60. This will be 30. At this point, light is incident. It is changing medium. Okay. What will be angle of incidence here? What will be angle of incidence? This angle here is 60 degree. Okay, let me write it this way here. Okay, this angle here is 60 degree. This angle is more than critical angle. It is more than critical angle. So light will not go into the other medium. Not possible. Light cannot go into the other medium. Okay. In that case, there will be total internal reflection. Light will be reflected. Light will not be refracted, but it will be reflected. Laws of reflection will be applicable. This is 30, okay. This also is going to be 30. This will be 30 and this will be 60. This will be 60. Okay, makes sense? Now this is 30. Light will be reflected like this. Okay. This will be 30 here. This angle is 30 degree. Okay. This is also 30. Okay. This is also 30. So what will be angle of incidence here? Angle of incidence here at this point. This is 30. This angle is 30. So this whole thing, this thing becomes 60 degree. Okay. What will be this? This will be 30 degree. Does that make sense? Okay. Again at this point there is change in medium. Again medium changes. Again there is change in medium here. Here also light is going from denser to rarer. Denser to rarer. There is a chance of total internal reflection. I will compare this angle angle of incidence here with critical angle. This angle is smaller than this. Smaller than this. That means light will be transmitted into the other medium. So it will be transmitted like this. Okay. This will be the final angle of emergence. Light will not come out from this slant surface, it will come out from this bottom here. Okay, and what will be this angle? It will be like this. This is mu is 5/4. 5/4. Okay, so I will write here 5/4 and sine, this is 30, sine 30 is equal to, this is mu 1 and sine E. Okay. What will be sine E? Sine E is going to be equal to 5/8. Now this is not a standard angle. This is not a standard angle. I have to find deviation. How do I find deviation? Okay. The best thing to find deviation is to find deviation in each step. Okay. In each step. This is first step. This is the first time deviation happens. Okay. This was my original direction of propagation. Okay. Light finally goes in this direction. Okay. So the first deviation happens here. This is delta 1. What is delta 1? What is delta 1? Okay. This is 30. This also is 30. And this is 30. Okay. This angle here, this angle we found out, laws of reflection. This is 30, this will be 30. Now, if you consider this line, this whole line here, this is 30, the opposite angle here also, this will also be 30. So 30 and 30, it will be 60. 30 degree plus 30 degree, this is equal to 60 degree in clockwise direction. In clockwise direction. Okay. Now, think about here. This was my direction original here. Now, the light deviates in opposite direction, anti-clockwise. Okay. What will be delta 2? It will be equal to, you see, this is 30. So this angle here is 30 degree. This is going to be equal to delta 2 is going to be equal to E minus 30. What is E? Sine inverse 5/8. Sometimes we get such type of answers. This is not a standard value. This is not a standard value. Okay. So we have to take it as it is. So sine inverse 5/8. So this will be equal to delta 2 will be equal to sine inverse 5/8 minus 30 degree. Now this angle, this is in anti-clockwise direction. This is clockwise, this is anti-clockwise. What is net deviation? Net deviation. Okay, so this was a little difficult problem. Okay, delta is equal to delta 1 plus delta 2. Okay, do you see this? Do you see this? This is going to be equal to, both are in opposite direction. One is towards right, the other one is towards left. I want to add both. Okay, so I will actually have to subtract it. I am going 10 steps forward, 3 steps backward. What is net displacement? 10 plus minus 3, that will be 7. Okay, it's like this. It will be equal to 60 minus, okay, minus of, this is sine inverse 5/8 minus 30, and this whole thing will be clockwise. Okay, this will be 90 minus sine inverse 5/8. This is my answer. This will be clockwise. This is my answer. Okay, with little bit of logic, you could have got the same answer. It's like this. Okay, note down this answer. We are going to solve this in a different way now. Okay, it's like this. Okay, let's do it like this here. Okay, the same thing I could have got in a different way. It's like this. This is my prism. Okay, light enters here. It is reflected like this. Okay, This was the original direction. This is my original direction. It is parallel to this base. These two directions are same. Okay. Now light finally comes out. This is a normal. This is a normal. It comes out in this direction here. Okay. This is angle E. Okay. So light was initially traveling in this direction. It is same as this direction. So I can say that light was traveling in this direction, and finally it goes in this direction. Okay. So this is the deviation. How easily I got it? Delta is 90 minus E. That's it. I have this answer. 90 minus sine inverse 5/8. This will be clockwise. And this is my answer. Exactly same answer that we got. Okay? Think about it. Now the next one. Okay, how do we solve the next one, second problem and third? Okay. Fourth, fifth, okay, all these problems are of same type. Okay. Some data is given and some condition is given. Light should not enter that medium. Light should not come out from that medium. Light should not come out from this surface, upper surface. Light should not enter into this. Okay. All of these are basically related with critical angle only. All of the problems. Okay. Let's try to solve first one. Let's try to develop some theory. Of course, we have the theory. Some easy method to solve it. Not tricks. Okay. Some direct methods. Some easier method. Okay. Where I can solve such problems directly without much calculation, without applying too much logic. Okay. Let's start with this one here. Okay. Let's start with a general case. I have this medium mu1. It is equal to 4/3. Okay, this is water. This medium I want to find. It is oil. I want my light not to enter this medium. I do not want this to enter. Okay, it's like this. Okay. This is angle of incidence I. Okay, understood? It is 60 degree. In this case, it is 60 degree. It is 60 degree. Maximum refractive index of oil such that light does not enter it. I do not want my light to enter this. That means I want my light to be reflected. I want my light to be reflected. Okay. In the critical case, it will move along this interface. This is the critical case. This light is just about to enter this, or it just is stopped from entering this medium. Both statements are actually same. Okay. Both statements refer to this condition. Okay, when this angle is 90 degree. So I can directly apply Snell's law and get the answer. Okay. Now let's do it in a little different way. Okay. It's like this. For light not to enter other medium, okay, that is oil here. I have this oil here. Okay, there should be total internal reflection. Okay, that is angle of incidence should be more than critical angle. Well, okay. Now, one other thing. I can stop this light entering into this medium only if this is a rarer medium. If this is a denser medium, I cannot stop it from entering. It is always going to enter. Okay. This happens only when light goes from denser to rarer. That means this is a rarer medium. This is a rarer medium. Okay. Angle of incidence should be more than critical angle. In that case, it will happen. Total internal reflection will take place and light will not enter oil, the other medium. Okay. I can also write it as theta c is less than I. Okay. Now sin theta c is less than sin I. Does that make sense? Sin theta. So what will be sin theta? What will be critical angle here? This is the rarer medium. This is the denser medium. Okay. So mu2 over mu1 should be less than sin 60. This is sin 60. Angle of incidence here is 60. Okay. That means mu2 is less than, okay, mu1 sine 60, okay, so mu2 is less than mu1 4 over 3 times root 3 over 2, okay, that means mu2 should be less than 2 over root 3. The refractive index of this medium, it should be less than this, any value but less than this. That means this is the maximum possible value, okay, we write it as mu2 maximum is equal to 2 over root 3, maximum possible value, okay. That's how we do it mathematically. This we have to keep in mind. But we are not always going to do it in this manner. I have a simpler method. What is a simpler method? It is talking about maximum or minimum in all the problems, whether it is maximum or minimum. Okay. Whenever you read this statement, find maximum, find minimum, find maximum. That means it is a critical case. Light is just about to enter, but it does not enter. That means it goes tangentially. It passes parallel to that medium. Okay. In that case, I already know that this angle is going to be 90 degrees. And that's it. Okay, I will write this. Mu1 sine theta 1 is mu2 sine theta 2. Okay. This is 4 over 3 sine 60 is mu2 sine 90. I have this answer, direct answer, okay? So this mu2 is going to be equal to 4 over 3 into root 3 over 2, 2 over root 3. This is my answer. So whatever it is asking about minimum or maximum, okay, I do not really have to think too much about it. I simply apply this condition, I get the answer. Okay, now try applying this condition directly and answer all these things, okay? All the questions here. Can you do that? Of course you can do that. Okay, let's do it together. Or you can do it yourself. That's much better way of doing it. And then we can discuss it together. Okay, now we are going to discuss it. So this is incident normally. It is incident normally. Okay. I do not want it to come out of the slant face. It does not come out from the slant face. I do not want my light to come out from this face. That means there should be total internal reflection here. Since I want to find minimum or maximum, that means it is the critical case. Okay, in the critical case, light will pass tangentially like this. Critical case. Okay, so this is going to be 90 degree. 90 degree. This mu I have to find. This angle is 37. 37. This will also become 37. Okay, here I have air. Air, mu is 1. Okay, so mu sine 37 is equal to 1 times sine 90. I have this answer. Mu is 5 over 3. This is the answer. This should be the minimum value of mu. Minimum, at least this much. Minimum this much. If it is more than this, that's fine. But it should not be less than this. Okay, in that case, light will never come out from the slant face. It is going to be totally deflected. In the critical case, it will pass like this. Okay, let's apply this critical case condition. In all the cases, we can find our answers pretty easily. Okay, do that in the next two problems. Okay. Again, maximum, minimum. The moment you see this, you have to apply the critical case condition. Okay, light passing tangentially. Angle of refraction 90 degree. Light enters here. What should be maximum value of this such that it never comes out from the upper face? This is the upper face. Okay. So in the first part, in this first question here, I do not want my light to come out from this. In the critical case, it will pass tangentially. Here also, I do not want my light coming out from this. In the critical case, it is going to pass tangentially like this. In both cases, you just apply the condition of this critical case at this point here, and you have the answer. Okay, it's like this. Let's do it in the first case. And do you know what it is? Let me solve it. Then we are going to see what it is. Okay, a beautiful, a very important, very important application of total internal reflection that we use it all over the world. This is used. It is known as this. A particular thing is known as OFC. OFC, optical fiber cable. Optical fiber cable. Okay, that's how we get our broadband connection in our homes. We have a server somewhere, situated somewhere, I do not know where it is. In my home, I am getting this internet connection. Actually, I am getting EM signals, EM wave signals, electromagnetic waves. It's same as light. Whatever we are discussing is for EM wave. It is applicable for light, for X-ray, or any EM wave. Okay, whatever we are discussing is for every EM wave, not only for light. Okay. So here is my server. It sends my signal. I choose my mu1 and mu2 such that no matter what happens to the cable, okay, even if my cable is in this shape, here in this case also, okay, if I have suitable values of this mu1, which is known as core, outside here is cladding, a thin layer of covering. It is wrapped, surrounded by this cladding. mu1 and mu2, if they are suitably chosen, okay, so once the light enters here, it is never going to come out. Okay, it will keep on getting reflected and it will reach the other end like this. Okay, that's how the optical fiber cable works. It is also used in medical field, like many instruments, like endoscopy. Okay, they insert a thin tube inside your stomach through your mouth. Okay, at the end of that tube there is a camera. That camera captures the photo. It comes out through this cable out of your mouth. It goes into the computer. Doctor sees it. Endoscopy, optical fiber cable. Both are based on this concept of this not concept. It is not a concept. It is a property, actual physical thing. Okay, total internal reflection. Okay, so here we have. So we are going to apply this critical case condition here at this point. Okay, so light enters here. It enters at some angle I. Okay, it gets refracted, and again there will be. It is going to pass like this. I do not want my light to come out from this. So this is the critical case. Okay. All right. Let's say that this angle is theta. This angle is theta. Okay. What this angle is going to be? This will be 90 minus theta. It's a rectangular slab. It is going to be 90 minus theta. Now this is the first point where reflection happens. This is the second point where reflection happens. Mu is given under root of 7 over 2. Okay. Let's apply our Snell's law. Snell's law at point 2. Let's start with point 2. At point 2. How will I write my Snell's law? I will write mu sine theta is equal to 1 times sine 90. This is air. Okay. I get sine theta is 1 over mu. Okay. Makes sense? This is going to be equal to 2 over root 7 sine theta. Now, at point 1, I am going to write 1 into sine I is going to be equal to mu times sine 90 minus theta. This angle is 90 minus theta. It becomes cos theta. Mu cos theta. Now, if sine theta is 2 over root 7, what is cos theta? Cos theta, under root of 1 minus sine square theta. Okay, so under root of 1 minus 4 over 7. This becomes under root of 3 over 7. Under root of 3 over 7. Okay, mu, what is mu? Mu is root 7 over 2 times under root of 3 over under root 7. That's how we do it. Okay. Can you do it in the same manner here? Here also. I'm sure you can do it. Okay. And you can get the correct answer in your first attempt. Okay, let's see. So critical condition we have to apply, and that's it. Okay. So let's simplify this figure. I can draw my figure like this. This is core, and this is my cladding. Okay. This is my cladding. This is mu2, mu1 here. Core and cladding. Okay. I have this light entering here. This is I. Okay. It gets refracted. At this point, I do not want light to enter here. In the critical case, it will pass like this. That is acceptable. It should not enter. It can pass tangentially. That's fine. Okay. But it should not enter here. Let's say that this angle is theta. Okay. This angle will be 90 minus theta. That's it. Okay, let's apply it here. This is point A, this is point B. Let's apply it first at point B. Snell's law. Mu1 sine theta is going to be equal to mu2 sine 90. Okay, what is sine theta? Mu2 over mu1. That's it. It is critical angle. This is critical angle. Rarer over denser. Okay. Of course, mu2 should be less than mu1. Okay. It goes without saying. Okay. Now, at point A, this is air here. It is air. So 1 times sine I, okay, is equal to mu1 times sine 90 minus theta. 90 minus theta. This becomes mu1 cos theta. Mu1 under root 1 minus sine square theta. Okay, so this becomes mu2 square over mu1 square. Okay, what do I have? Very nice answer. A nice answer. You see, it's like this. Mu1 square minus mu2 square. This one gets cancelled. Mu1 gets cancelled. Okay, so sine I. Sine I is under root of mu1 square minus mu2 square. A very nice thing. Okay. This is my answer. So I can write I, sine inverse of this thing. That's how I should decide my mu1 and mu2. Okay. So light will not enter. For this, my maximum angle is this. This is the maximum angle. Now, if angle is more than this, then it will start entering. Okay, so in this case, it will not enter. Okay, this angle is critical angle. Try to understand this. A very important question I am going to frame, and that you will answer. I will not answer. You will try to answer it. I am going to give it in your problem sheet. A very important question I am framing. Okay, right here. We calculated this angle. That means this is 60 degree. If angle is 60 degree here, then after deflection this becomes critical. It becomes critical, and then it does not enter. It does not go out. I am saying that this is my maximum angle. Angle should not be more than 60. What if I increase this angle? Now, if I increase this angle, let's see. If I increase this angle, then this angle is also going to increase. It is also going to increase. Now compare this and this. If this is critical angle, then this angle becomes less than critical. For this light, this is light 1, light 2. For this light 1, okay, this is the corresponding reflected light. This is 1. This becomes 2. Corresponding to light 1, here this angle is critical angle. Now if I increase my angle, this is more than, this thing is more than 60, then what will happen? Then this angle, it's clearly seen, it's obvious, I do not really have to explain too much, this becomes less than critical. This angle will be less than this angle. This is less than critical. Now the light starts going into the other medium. It will start going into the other medium. Now I want to stop that also. I want to stop. I do not want this happening. I want to design a system such that I want to design an optical fiber cable. I want to design this such that no matter what is the angle of incidence, I want to design a system, I want to design my cable, I want to design this, I want to choose my mu. Okay, what should be mu? What should be mu such that no matter what is the angle of incidence, no matter what is the angle of incidence, light should never get out of this system. For that to happen, what should be mu? What should be the minimum value of mu for that to happen? Okay, now can you answer that? You will see one problem, same problem in the same problem you will see, okay, in the problem sheet. Try answering that. Okay. Now, this phenomena, total internal reflection, has some very important and interesting also application. One of the very important application is this one here. Let's look at some interesting things associated with total internal reflection. Okay, it's like this. Okay, consider that this is a swimming pool. Okay. Imagine a swimming pool filled with water up to some height, and it is dark outside. Okay. Dark night. Okay. It's pitch black dark. Okay, no source of light anywhere to be seen, nothing. Okay, and then in that dark night, inside the swimming pool, I keep a light bulb here. A very small source of light. A light bulb is here. A light bulb. Let's see the interesting thing. Very interesting thing. It's like this. So this light bulb will send light in all the directions. Okay. Let's consider one light here. It is incident normally. This is the interface. This is the interface of water. This is water, swimming pool, it's water. It is air here, outside is air. This is my interface, the surface. Okay. The light which is incident normally, it goes out without deviation. Without deviation. Look at any other light here. What will happen to this? It will refract to the other side, into the air. Okay. Now keep considering such light rays. Now when you go away, this is the central point here. When you go away from it, what is happening to this angle? Look at this angle. This angle keeps on increasing as I go away from this point, which is directly above my bulb. Okay. The angle keeps on increasing. At some point, it will become equal to critical angle. Do you see this? Light will come out from here, but here light will pass tangentially. As I go away, this angle keeps on increasing. At some moment, it will happen that it becomes equal to critical angle. Light is going from denser into rarer medium. It is critical angle. Now, what will happen after that? Okay, if you consider any other light which is incident after this point, it is going to be reflected back. Okay, it is never going to come out. So this is the boundary. Okay, the light is going to come out only if it is between this region, in this region. If the light hits a point after this, it is going to be reflected. It is going to be reflected. Okay, same thing will happen on the other side also. Okay, this is my critical angle. This is going to be, it is going to pass tangentially. Any light after this is going to be reflected. Okay. Then if I am looking from outside, I will see light coming out from this region here, from this region here, but I will not see any light coming out from points after this. Okay. So I will see a circular illuminated area here, a circular patch. Light will come out from this circular region only. Outside this region, it is completely dark. It is completely dark. Do you understand this? Okay. Now let's solve one problem based on this. Okay. I have this light bulb here. Light bulb. And this is my, let's say, water. Height of water is 2 meter, let's say. 2 meter deep swimming pool. Okay. And this is water, is 4/3. The question is, what area on surface of water appear illuminated? Appear illuminated. What do you think? Try to answer this. Okay. And then we are going to look at many interesting, few more interesting phenomena associated with this phenomena, that is total internal reflection. Okay. Let's see what answer you get. Can you solve it? Okay. You have to just apply the concept of critical angle. Okay. So I'm going to solve it now. Before I do, try to get the answer. Otherwise, I'm going to spoil, okay, all your fun. That's what I do. Okay, this is my central line here. Just take off the bulb. Okay. Let's say that this is my critical angle. This is my critical angle here. Okay. So light will come out from this region only. This is on the other side. Okay, it will be on the all sides. Okay. With respect to this, all these points will be on the circle. Okay, on a circle of radius r. Let's say radius is r. Okay. So light is going to come out only from inside this circular area. Okay, do you see this? Okay. Outside of this, light is not going to come out. It is going to be reflected back into the pool. This is 2 meter. Let's say that this is height. This is height h. This is mu. Okay. What is sine theta c? Is equal to 1 over mu. Okay. Do you understand? This is 1. This is mu equal to 1. Air. Rarer over denser. 1 over mu. What is tan theta c? Tan theta c is r over h. So r is h tan theta c. What do I get? I get radius of that circular region from which light comes out. Only that part will appear illuminated. Outside of that, complete dark. No light will come out from that outside region. I know sin theta c. Using that, I can find tan theta c. This is 1. This is 1 over mu. So this is 1. This is mu. This becomes 1 plus mu square. So what will be tan theta c? Okay. R will be equal to h. Tan theta c here will be equal to, this is sin theta c, 1 over mu. This becomes 1 over mu square. Okay. I want, I think that's a mistake, a big mistake here. Sin theta c is 1 over mu. So this is 1, this will be mu. This will be under root of mu square minus 1. Okay. So what will be tan theta c? Tan theta c will be 1 over under root of mu square minus 1. Okay. That's it. We have radius. Okay. What is radius? 2 meter. It is 2 meter over under root of mu square 16 over 9 minus 1. Okay, this will be equal to 2 times 3 over root 7 meter. Becomes 3 and 2 becomes 6 over 16 minus, okay, I do, okay, of course I'm doing this wasteful thing. So what is area? What is area? I want to find area. A is pi r square. Okay, so pi into, this is 6 square. So 6 over, so 36 over 7. 36 over 7 meter square. So this much area on the surface of water appears illuminated. This is my answer. Okay. Do you understand this? I hope that I made all the calculations correctly. Sin theta c 1 over mu. So this is theta c. This also becomes theta c. Then I am writing tan theta c, r over h. So r will be h tan theta c. Sin theta c is 1 over mu. So this becomes tan theta. Okay, I think I am doing it all right. Okay, I am doing it perfectly all right. That's fine. Okay. Now that's how I will see a circular patch. Okay. Now let's consider one other very interesting thing. Try to understand it. What I said, that I have a swimming pool and it is night time. It is night. Okay, completely dark. In that case, light will come out only from this region. Only from this region. Light will come out. Okay. Now what will happen if it is a daytime? If it is daytime, now consider this, daytime, light comes out only from this region. It cannot come out from this region here, it is going to be reflected back. It is going to be reflected back. Now, if it is daytime, use reciprocity. Okay. I can reverse all the light rays. Okay. This light ray is coming out, starting from here. They want to go out. Only few of them can go out, not all of them. They will go out from this region. Okay. Now, if I reverse it, so it is daytime. Light is coming from all the directions. Light is coming from all directions. Light is coming in this direction. Light is coming in this direction. It is coming in this direction. Okay. Now, out of all those light, okay, not all the light can reach this point. Only few light rays can reach this point. Okay. Light ray coming from this direction. This will be able to reach here. Light coming in this direction. This light will be able to reach this point here. Let's say that I am standing here. I am lying here on the bottom of this pool. I am here. This is me. I am lying here. Or let's say it is you. You are lying at the bottom of the swimming pool and you are looking up. What you will see is that light is coming out from a certain region only. The rest of the swimming pool appears like a mirror. You will see that there is a hole. On the surface of water, there is a circular hole from which the light is coming out. The light is coming. And the remaining surface will be a mirror. It appears like a mirror to you. Okay, so when you go down and lie here at the bottom of this swimming pool, and if you look up, you will see a circular hole. Light is coming through that circular hole. Outside of that circular hole, it appears like a mirror. It will be a mirror, okay? Try to imagine this thing. Okay. And not only that, okay? One other interesting thing. Okay. In daytime, light comes out from all directions. All directions. Imagine this. Look up. Try to scan the whole sky. The whole sky. Let's say that this is my Earth, and this is I am standing here, and this is my horizon. This is my horizon. This is my horizon. Okay. This whole thing is my sky. It's my sky. Okay. I want to scan. I'm standing here. I want to scan the whole sky from east all the way to the west. By what angle I will have to rotate my head to do that? Suppose I can rotate my head freely by 360 degree. Imagine that I'm an alien. I want to scan the entire sky from east to the west. By what angle I will have to rotate my head? Of course 180 degree. Okay. I will have to start looking from here. I will have to look all the way from east to west. I will have to rotate my head by 180 degree. But see the beauty here. This corresponds to east. This corresponds to west. Okay? The light from east direction. It is light from east direction. It is entering my head here. It is entering my eyes. This light is entering my eye. Light from west also is able to enter my eye. Now, if I want to scan the whole sky, I will have to rotate my head only through this angle. Only through this angle. That's it. This will be 2 theta c. I want to scan the whole sky standing in air. I will have to rotate my head 180 degrees to go from east to west to see everything in the sky. And see this beauty here. If I'm inside water, I will have to rotate my head only few degrees, not 180. It depends on critical angle. If I rotate my head, if I rotate my eyes only through this angle, it will be equal to 2 times of theta c. I will be able to see everything from east to west. I will be able to scan the whole sky just by rotating my eyes only through this angle. Okay. One very interesting application, okay, of this phenomena, total internal reflection. Okay, one last thing that we are going to discuss. There is something that all of you must have heard or seen also. I'm sure about that. You must have seen it. You must have heard about it. It's known as mirage. Okay, imagine a hot summer day. A very hot summer day. You are driving on a highway. On a very hot summer day. Driving on a smooth, flat highway. Sometimes it appears. Sometimes you see the image of a vehicle which is running in front of you. You see its image on the road. The road appears like a mirror. It appears as if there is water on the road. And the fun thing is that when you reach that spot, you don't find water. Then water appears at some other distance. Okay, and it keeps on happening. Generally, it happens in summer days when it is very hot. That thing is known as mirage, and it's a very common phenomenon in deserts, in hot deserts, not the cold deserts, but the hot ones. Okay, in the cold one, the opposite, of mirage can be seen. Opposite of mirage. We are talking about the normal desert, that is the hot desert, very hot. Okay, you are traveling in a hot desert. At some distance, you start feeling as if there is a pond, a water body. You see the images of trees. Okay, the inverted image. It appears as if there is some water, but the moment you reach there is nothing. And many animals keep on running throughout the desert just in search of water. Okay, it's known as mirage. Now, how it happens? Okay, let's try to understand it. It has to do with critical angle, and total internal reflection. Okay, let's see how it works. Okay. Let's say that this is my a very hot surface. Okay, very hot surface. Okay. Above this, I have air. Air is of course it atmosphere. I have air. I can imagine air to be of different layers. Okay, there are different layers of air. These are the layers of air. One layer here. I'm just drawing this schematic diagram. Okay, I can imagine that there are several layers of air. Of course, there are. We can do that. We can imagine my atmosphere to be made up of different layers. Okay, there's no problem in this. So here, these are the layers of air. Okay, this is the surface, Earth. It's very hot, very hot. So the layer of air which is in contact with the surface, the first layer which is in contact, very hot. Its temperature is equal to this temperature. Both are in equilibrium. But as we go up, temperature decreases. Okay. As we go up, temperature decreases. And when temperature decreases, density of air increases. Density of air. And refractive index of air changes with density. So when density increases, refractive index also increases. Remember this relation. As we go up, temperature decreases. As a result, density increases. Mass by volume, that density. And because of that, the refractive index of air also increases. You see, refractive index of air is not 1. It is just approximately 1. Okay. But here we see the variation in the refractive index as we go up. The refractive index of different layers, it increases. Now imagine one object here. Imagine that I have one object. It's a tree, or it can be a building, or it can be a vehicle, anything. One object here. From this object, light rays go in all directions. Let's try to find out what happens to a certain light, okay, which starts moving downward. Okay, imagine what happens to a light which starts moving downward. As it moves downward, okay, this is my light ray, one light ray starting from this point. Okay, the same thing will happen with every point. We are considering the light rays that is moving downward. Okay, this is angle of incidence. As the light rays come down, it encounters a rarer medium. The upper layers are denser, the lower layers will be rarer. So as compared to this layer here, this layer is going to be rarer. Okay, so this is going to bend away from normal. It is going to bend away from normal. The angle of incidence increases. The angle of incidence increases. Okay. As it comes down, its angle of incidence will keep on increasing. Okay. The angle of incidence keeps on increasing. Okay. At some time here, at some point here, this angle of incidence, it becomes more than critical angle for these two interfaces, for these two mediums. Okay. So as the light rays come down, they are traveling downward. As they come down, they are encountering rarer mediums. Angle of incidences, and these angles will keep on increasing. Okay. The light will keep on bending away from normal. Okay. This light ray is bending away from normal. These are the normals. At some instant, it is going to happen. It happens. Okay. That's why we have this phenomenon. This angle becomes more than critical angle. Then it starts going up. It starts going up. Okay. Now, if you consider two light rays, okay, then the same thing will happen with them. Okay, they will start, they will keep on moving. Okay, they will keep on, okay, traveling away. Okay, it's like this. Okay, so the light rays start going backward, upward. Okay, and if there is some observer here, let's say, if there is some observer, so these light rays, they reach the eyes of observer, and this observer, so these light rays are reaching the eyes of this observer. Okay, so this observer will see, will feel, experience as if these two light rays are coming from point somewhere here. Okay, so what I have actually is an image of this object. Similarly, the image of this entire object is formed, an inverted object. Okay, so this observer, this person feels as if there is a mirror here. This surface appears like a mirror. It appears like a water or still water surface. This is known as mirage. Okay. Okay. So that's it for this lecture. Okay. Next class we are going to start a new topic. Okay.